Hello, everyone. Hello, everyone. Thank you very much for joining us today for this webinar, jointly organized by International Renewable Energy Agency, IRENA, and China Electric Power Research Institute, CEPRI. My name is Arina Anisie, and I am from International Renewable Energy Agency at the Innovation and Technology Center in Germany, Bonn. I will be moderating today's webinar together with Hyuming Zhang, secondee at IRENA from CEPRI. Let me first start by saying a few words about what IRENA is. IRENA is an intergovernmental organization with currently 168 member states and another 16 countries in their accession process. We support countries in their transition to sustainable energy future and serve as a principal platform for international cooperation, a center of excellence, and a repository of policy, technology, resource, and financial knowledge on renewable energy. Earlier this year, we released the report on grid codes for renewable power system. The study focuses on the latest development and good practices to develop grid codes for power systems with high share of variable renewable energy, such as solar and wind. Today, we have the pleasure to launch the Chinese version of this report, kindly translated by CEPRI. During the course of today's event, you will listen to insights from experts from China and abroad on what grid codes are, how they are key in supporting the integration of high share of renewable electricity in the system, while also maintaining the stability of the power system. But before we start with exciting program for today's events, we are delighted to have the senior management from CEPRI and IRENA providing us with some introductory remarks. With no further ado, let me please give the word to Hyuming Zhang from CEPRI. Hyuming, the word is yours.
好的，谢谢 Irena。
Thank you, Irena. Honored distinguished guests, I am Zhang Huiming from CEPRI. I am also a loan officer in the innovation and user team of the ITC. I am very happy to host this webinar with Irena. Next, let's welcome the president of CEPRI, Mr. Zhao Peng, to deliver his opening remarks. Honored Mr. Roland Roche, distinguished participants, experts, scholars, and youth from ITC and around the world. Hello, everyone. I am Zhao Peng, the president of the China Electric Power Research Institute. First, on behalf of CEPRI, I would like to express my warm congratulations to the start of this meeting. I would like to sincerely thank Mr. Roland and our partners from the ITC and friends from the State Grid Corporation of China, and NSO-E, Imperial College of London, Tsinghua University, North China Electric Power University, Nestor, DII, EDF China R&D Center, and other participating organizations for your support. A special shout out to the ITC, our partner, for your hosting and guidance of our research fellow, Dr. Zhang Huiming, who is currently serving as a loan officer. Global climate change is an urgent threat, as is carbon emissions to the environment we all rely on. Therefore, tackling climate change and climate crisis, achieving carbon neutrality and developing clean energy and promoting green production lifestyle are key for these vital times. There is a more consensus around the world energy transformation. Clean energy leads this transformation that centers around electric power, promoting large-scale development and economic and efficient clean energy utilization are now the global focus. China has announced our intentions to actively reach peak emissions and carbon neutrality. To this end, great efforts have been made to build a new type of power system, or NTPS, whose design centers around renewable energy as its main body. China ushered in a new round of sustainable and rapid growth of renewable energy and renewables, with wind power's photovoltaic installed capacity and power generation ranking first in the world. The cost of development for renewable energy is declining. Wind and power solar PV generation has entered a new stage of market-oriented development in China. a stage of no subsidy at fair pricing. Tackling the issues of creating RE-friendly grid with high integration is a key to the development and utilization of renewable energy all over the world, and it is a key for China to build NTPS. The ITC-led Grid Codes for Renewable Power System combines technical achievements and best practices of major countries and regions around the world in renewable energy grid integration. This forward-looking report examines the trend of the global power grid guidelines, serving as a good reference for the guidance and promotion of RE grid integration technology in China and the support of NTPS. In order to share the relevant experiences and methods with many people and countries as possible, our institute has gathered an interdisciplinary task force of more than 10 experts. And with the support of ITC, we completed the entire compilation of translation in half a year. Today, we are proud to jointly host this press conference, this launch of the Chinese version of the report of the ITC, and invited experts and scholars from internationally renowned enterprises, research institutions, universities, organizations, and grid operators to exchange views on the renewable energy development trends, grid integration technologies, guidelines, and standards, and trading mechanisms. Pooling our minds and ideas, we can discuss how to raise RE grid integration ratio and scale, as well as efficient utilization by sharing RE development best practices from around the world. CEPRI is a multidisciplinary and comprehensive science research institute in China's electric power industry. Our research covers electric power science and related fields, including key power grid technologies such as safety analysis, operation control, large power grids, UHV, AC, DC transmission, large-scale RE access, and large-scale energy storage. Many of our research stands at the forefront of their respective field. At the same time, CEPRI is also the main research arm for the research of the NTPS of State Grid Corporation. At present, according to the central deployment of the SGCC, we are carrying out in-depth NTPS technology R&D, equipment design, engineering, demonstration, and standard setting. CEPRI has attached great importance to international cooperation. We are eager to strengthen ties with our international counterparts and build a platform for exchange and cooperation. We would like to share and learn from advanced ideas and development experiences and continue to contribute to the global energy contribution. ITC is an important technical support arm for IRENA strategic research. It has a lot of commonalities and overlaps with CEPRI's strategy and mission. Under the auspices of the MOU between State Grid of China and the IRENA, in recent years, our institution and ITC has carried out in-depth practical cooperation in many aspects, such as technical exchange, joint research and information campaigns, personnel training, platform construction. We're delighted for these achievements. We have dispatched 2 rounds of visiting scholars to IRENA, with Dr. Zhang Huiming just recently receiving an extended term to expand his learning opportunities for an additional year. A top-level expert still selected to provide support for the preparation of relevant support. Our partnership have jointly held the first CEPRI and ITIC international seminar, and our social media platform launched an international focus column to publish and share important opinions from the ITC experts and to spread awareness to more parts of the world and improve international leadership. I believe that the launch of this report and the hosting of today's seminar will play a good role in promoting continuous deep cooperation between our 2 organizations. We look for further pragmatic cooperation with the ITC in joint research and experience sharing in the future. And we also hope to continue conduct exchanges and discuss with other organizations, institutions, and scholars from all over the world who are attending today. Together, we can make new contributions to promoting energy transition, coping with climate change, and achieving sustainable human development. Finally, I would like to wish this meeting a resounding success. Thank you all. Now, President Zhao has just introduced our work in the translation of the report and editing of the report. And we are currently collaborating with these ITC for the past 2 years, focusing on the importance and of the collaboration in the context of global energy transition. Thank you, Mr. Zhao, again, and for your warm welcome.
Thank you very much also from my side, Mr. Zhao Peng, for the opening remarks. Now I am pleased to give the word to Mr. Roland Roche, the director of IRENA Innovation and Technology Center in Bonn, for his opening remarks. Welcome, Roland.
Yes, good morning, good afternoon. Thank you, IRENA. On behalf of the International Renewable Energy Agency, I would like to welcome you all to this virtual event co-organized with the China Electric Power Research Institute, CEPRI, which is part of the State Grid Corporation of China. I'm particularly excited on today's launch of the Chinese version of our analysis on grid connection codes. This analysis is the result of a fruitful cooperation with CEPRI, and it provides up-to-date information and guidance on how to design, develop, and implement grid connection codes that enable renewable-based power systems to operate in a cost-effective and reliable manner. IRENA has been working with its partners in supporting countries in transforming their power system while reconciling two key macro objectives. First, having a low carbon system, and second, ensuring the affordability, reliability, and security of electricity supply. Our analysis shows that achieving those objectives is feasible and cost-effective if the power system transformation is planned, designed, and implemented, taking onto full consideration the latest innovations in technology, market design, and system operations. One of the key tools available to ensure a sound operation of power systems dominated by renewables are grid-connected codes. IRENA's report on this topic highlights the evolution of grid codes in a changing power system towards a more decentralized and digitalized system. Grid codes build trust between system operators and stakeholders. They are critical enablers to ensure the security of supply. This report highlights examples from countries which have been pioneers in the integration of variable renewable energy sources, including China. I would like once again to express my sincere gratitude to Mr. Zhao Peng and CEPRI for the excellent cooperation to conduct this work and also making it now available into Chinese. CEPRI has been supporting our work since the past years, also with a secondment, and it's proven to be a very effective collaboration between CEPRI and IRENA. Thank you again, and I'm looking forward to today's discussion and presentation from a large number of experts from China and Europe. Thank you very much.
Thank you very much, Roland. Xiuming, the word, it's yours now.
好，谢谢 IRENA， 谢谢罗兰主任。下面是今天的主旨报告环节，让我们有请中国电
Thank
科
you very
院
much. Now, let's give the floor to Mr. Li Peng, the Executive Vice President of CEPRI. His topic is Challenges and Key Technologies of NTPS.
共享好了吗？ Okay. Good afternoon, everyone. I'm Li Peng from China CEPRI. It's my great pleasure to make a keynote speech here. The topic of my presentation today is changes and the key technology of new type power system. This slide is about my personal profile. My presentation covers 4 parts. First of all, I'd like to brief on the concept of NTPS on the energy transition. To tackle the climate change, China proposed the goal of peaking carbon emission by 2030 and achieving carbon neutrality by 2060. From carbon peaking to carbon neutrality, the developed world has a transition period of 40 to 70 years. However, China has only 30 years. China takes the replacement of fossil fuel energy with non-fossil fuel energy consumption as the main solution to achieve its climate goals. China's share of non-fossil fuel energy consumption will increase from 16% in 2020 to over 80% in 2060. And its share of non-fossil fuel energy production rise from 34% to over 90% over the same period. Between 2035 and 2045, China's non-fossil fuel power production will be dominant in its generation mix. From 2045 and onwards, China's renewable energy power production and the non-hydro renewable energy production will play a central role in its energy mix. From 2012 to 2021, China reduced the energy consumption intensity by 26%, cutting primary energy consumption of 1.4 billion tons. Over the same period, China's renewable energy installed capacity increased from 313 gigawatts to 1,063 gigawatts, with cumulative installed capacities of hydropower, wind power, and solar power, each ranking top in the world. At the same time, China's renewable production rose from 960 terawatt hours to 2,480 terawatt hours. Power Systems endeavors to adapt to China's low carbon energy transition goals and meet new requirements. Major challenges have taken place in the production, consumption, and the utilization of energy. Major changes have adjustment to energy mix brings changes to energy production. Deep energy decarbonization changes the energy consumption mode. Improvement of energy efficiency changes the way of energy utilization. All this is bound to bring profound changes to power systems. That's why the building of NTPS is proposed. Secondly, I will talk about the features and challenges of NTPS. NTPS has 3 major features: accelerated production of clean energy, high electrification of energy consumption, and increased efficiency of energy utilization. NTPS will strongly support energy transition and climate goals and bring profound new changes to generation mix, load, grid structure, technical foundation, and operational features. The fundamental changes of main power sources brings huge challenges to NTPS in terms of power and production balance, system security and stability, and the deep decarbonization of energy and electricity. Next, let's move on to the third part, power system technology innovation and application practices. To address the challenges of NTPS, technology innovation and application practices of power system are in urgent need to promote renewable energy development and utilization, electrification, and system flexibility. Innovation will be made out of 4 major fields, including power grid, renewable energy, load, and energy storage. As for power grid technology, in terms of UHV transmission, State Grid has formed the both AC and DC hybrid grid structure and built 29 UHV transmission projects. State Grid long-distance trans-regional power transmission capacity is expected to total 300 gigawatt in 2025. Regarding the VSC HVDC and the flexible low-frequency transmission, Zhangbei VSC HVDC power grid demonstration project was put into operation in 2020. In 2022, China's first flexible low-frequency power transmission demonstration project was also put into operation, which promoted the zero carbon island. As for renewable energy technology, on forecasting, State Grid has developed a customized numerical weather prediction system for electric power meteorology and further established the centralized forecasting platform. The platform has been applied widely in China, covering more than 400 gigawatt forecasting capacity and over 6,000 forecasting sites. On controlling, Grid has established the real-time control head-wall-in-loop EMT platform to simulate 10 gigawatt level renewable energy transmitted through SCC HVDC or MMC HVDC. By leveraging the platform, stability issues like broadband oscillation on the transient voltage can be investigated. As for load technology, by 2021, State Grid has promoted more than 390,000 electricity replacement projects and a total of 7.8 million new energy vehicles had been registered in China, including 6.4 million EVs. State Grid has been exploring new model demand response and building resource pool for demand response. By 2021, State Grid has owned 37.4 gigawatt adjustable loads. As for energy storage, by the end of 2021, China has owned 36 gigawatt installed capacity of pumped storage and launched the 5 gigawatt electrochemical energy storage projects. The construction cost of electrochemical energy storage is expected to keep declining. Around 2030, the levelized cost of energy for battery might be much lower than that of pumped storage. Now, let's come to the conclusion part. To sum up, building NTPS serves as an effective way to promote China's energy transition and achieves its carbon peak and neutrality goals. Innovations of source grid load storage and other key technologies is thus needed to address major challenges of balancing power and production, power system security and stability, and decarbonization of energy and electricity. I'd like to summarize it from the aspect of power grid, energy, power load, and energy storage. As for power grid, we need to focus on VHVDC and low frequency transmission technologies, which are suitable for transmissions of offshore wind power and large-scale wind and PV power in desert or Gobi areas. With regard to renewable energy, research into accurate power prediction and active supporting controlling of renewable energy is significant to the building of NTPs. In the aspect of power load, electricity replacement, demand response, related technical innovation, and need further promotion. Regarding energy storage, large-scale development of pumped storage need to be accelerated, and the performance and the cost-effectiveness of electron-chemical energy storage improved. That's all for my presentation. Thank you for listening.
好，谢谢李院长。李
Thank
院长
you,
刚刚结
Mr.
合
Lee.
结合双碳目标
And
介绍
just
了
now, Dr. Lee starts with the
新型电力系统的特征和挑战，
Dr. Lee
分别
starts with
从
the dual
燃网和储
carbon
等
targets,
方面
summarize the
提出了
characteristics and the
科技
challenges
创
of
新思路。
NTPS, and proposes the technical innovation
让我们再次感谢李院长的精彩报告。
from the aspects of source
下
network
面
load
我们
storage.
有
But
请
thank you
中国
again.
林科院
Welcome
电力系
to
统
the
Next,
director
let's
亚洲
welcome
和研究
the
中
Carbon
心
the
副主
coordinate,
任
the
Research Center
co-director
Xi
of
Yongning
Carbon
博士
Strategy
System,
Research
Dr.
Center of
Xi
Power
Yongning,
System,
接受
Dr.
第
Xi
二个
Yongning,
致辞报告。
to
keynote
deliver the second
presentation.
keynote presentation.
Topic
可再
is
生能源
topic
部网
is
的技术
progress
挑战
the
和
progress
标
in
准化。
international standards on renewable energy
international standards
integration.
on renewable energy integration. Let's welcome.
Good morning and good afternoon, ladies and gentlemen. I'm very pleased to have this opportunity attending the webinar and share some experience in terms of system challenges and international standardization on grid integration of renewable energy. Let's start from some background information on climate change. We know the driving force for developing renewable energy and energy transition is a climate change issue. Many countries have committed to achieving net zero emission by the middle of this century. And China also announced at the general debate of 75 session of United Nations General Assembly by President Xi Jinping that China aimed to have CO2 emission peak before 2030 and achieve carbon neutrality before 2060. With the growing of renewable capacity, the interaction between the large amount of renewable energy and power grid are dramatically increased. More and more issues and accidents happened during the past few years all over the world. Here, I would like to take some system accident actually happened on the power system to show the technical challenges and the risks of the renewable energy integration to the grid. The first event is a system level oscillation with wind power plant participation, which was recorded in Texas, in United States, 2009. Here is shown the diagram of the Texas power grid. The transmission line from Ajo to Netson was out of service, and Ajo wind farm connected to the ERCOT grid through a single transmission line, which was equipped with high series compensation. And in the case of a weak connection, a 20 Hertz subsynchronous oscillation happened, and leading to a 2 per unit over voltage on the grid, which causing a large amount of wind turbine tripping, and many wind turbines crewback circuit also be damaged. We can see the grid structure and the converter control play very important roles in this phenomena, which is quite different from the conventional SSO or SSR happened on synchronous machines. Another event is happened in South Australia, September 2016, when heavy rain and storm hit South Australia grid, caused system fault with 6 times 6 times successive grid voltage drop, and the local wind generation tripped, totally lost 950 megawatt power output. Also, the reverse of the load flow on the grid caused overloading and the disconnection of the tie line from South Australia to Victoria. And system blackout happened and lasting for 40 hours. Also, a frequency collapse was witnessed during the blackout. One of the main reasons is because operating wind turbines in this area are not equipped with the successive fault rise-through function and cannot withstand the successive system disturbances. The last system event I show here is a blackout in UK in the year 2019. The outage of Hornsea 1 offshore wind farm and a gas station during extreme bad weather, leading to the blackout, including area of London, and over 1 million people lost the power supply. The grid was getting weak because of the outage of transmission line. At a 10 Hz power oscillation, wind turbine tripping by overcurrent were observed during the fault. And also a large-scale distributed PV generation tripping because of the rate of change of frequency we call rock-off. The setting is too small. This system fault reminded the grid operator that the electrical behavior of wind power and distributed PV need to be improved. And also the system reserve for frequency regulation need to be considered carefully. Compared with the conventional grid structure, we also could see that the upcoming future grid with the capacity of fossil fuel power plant decreased, the rotating mass of a synchronous generator will be getting lower, which leading to a low inertial system with increasing risk of system frequency stability. Also considering the vulnerability, weak supportive function of renewable energy based on power electronics, and also the soft coupling between renewable energy and power system. The grid behavior will be dramatically changed, and mechanism of system synchronization also will be influenced. Beside the system fault and phenomena we already saw before, there are still more interaction which will be emerging soon, and we need to well foresee all these challenges. In China, with the quick development of renewable energy, conventional power sources are possibly to be replaced by renewable energy. In some provinces, more than 40% of total installed capacity are renewable energy. System inertia and frequency regulation capability continue to drop. The decrease of system inertia may cause a large drop of frequency and rock-off during the case of big power loss fault and impact the system frequency stability. For example, we can see by simulation that the system frequency drop is much lower than no wind case. Another more concerned issue in China now is the overvoltage at the sending side of the UHVDC transmission system. Main reason of UHVDC system communication failure are the low grid strength and voltage support at the receiving side. We also could see by simulation that the HVDC system computation failure could cause overvoltage at the sending terminal of AC system with around 100 millisecond duration. And 2 times successive commutation failure will last for 500 millisecond. Considering the potential overvoltage risk on the sending grid side, if the high voltage rise-through function are not equipped by renewable energy, the system will have a risk of wind power disconnection by overvoltage, even system blackout. In the scenario of high wind and solar PV penetration, the system performance will be dramatically influenced. For example, the system inertia, capacity for frequency control, and dynamic reactive power capacity are all declined. In order to guarantee the system stability, the full rise-through capability, controllability of wind turbine or solar PV panel shall be required. Many grid requirements to the renewable energy plant are presented by the grid operator, such as full rise-through, inertial response, voltage regulation function. Also, some of them are formulated into the grid code as well as technical standard. The last part of my speech mainly focuses on the grid code requirement and international standardization. For example, in USA, the Federal Energy Regulatory Commission issued order number 661, interconnection for wind power in 2005, presenting requirement to wind farms, including power factor, full rise-through, and SCADA systems. In 2015, NERC also published a framework report on essential reliability services to the grid, addressing inertial response, frequency regulation, as well as other requirements on controllability. In European country, the NSOE initiated an activity to harmonizing standard that generator must respect to connected to the grid. Those requirements that contribute to maintaining, preserving, and restoring system security in order to facilitate proper functioning of the internal electricity market within and between synchronous area should be regarded as a cross-border network issue and market integration issue. We also can see some requirement on frequency regulation capability is addressed. In China, the grid requirement to wind power was published in the year 2011 as a national level standard, which started to be upgraded since 2018 and finished the formulation by 2020 and published in the year 2021, incorporating some new requirement, including successive full rise-through, inertial response, and primary frequency regulation. For example, it says in this code, wind farm shall be capable of participating system frequency regulation with 10% up regulation headroom and 10% down regulation as a reserve. In terms of international standardization activity on grid integration of renewable energy, there is an IEC technical committee we call IEC SC8A, which was established in 2013, and its work scope covering the requirement for interconnection, related test for grid code compliance, as well as standard or best practice documents for planning, modeling, forecasting, assessment, control, and protection of renewable with a grid level perspective. I serve as the secretary from the year 2014, and by now, there are 8 working groups already being built up with 6 standards already published and 4 documents under preparation. Among these working groups, I also would like to highlight the Joint Working Group 5, which is led by Jason McDowell from GE and Professor Hu from Huazhong University of Science and Technology, covering several very interesting topics. For example, VKC grid connection, subsynchronous control interaction, fast frequency response, and so on. The final deliverables you can find and buy by the IEC store. The publication of these deliverables will bring more insight and values to the renewable energy society. Finally, I'd like to close my speech with a Chinese saying. The road before us is long and winding. Depart now, and we shall be arriving. This is also very suitable for describing the path to the future energy system with high renewable penetration. And we're also sure the technology innovation and standardization effort will help us to successfully pave the way to the brilliant future of net zero carbon. Thank you. Thank you very much for your listening.
Thank you, Dr. Chi. Dr. Chi has introduced us the the situation from China and international experiences in terms of power system inertia fall right through. Thank you again for your report.
分论坛一的研讨环节，主题是面向可再生能源电力系统电网导致的中文报告发布。我把
Next, we will come to the session 1. I want to give the floor to IRENA again.
Thank you very much for our distinguished speakers from CEPRI for the excellent setting the scene presentation. Now it's my pleasure to advance a bit in the agenda. We go into the session 1, which is a presentation of the report, which Chinese version was launched today, the Grid Codes for Renewable Power Systems, followed by a short discussion from a variety of experts on this report. So let me share my screen. Okay. So I will be presenting together with my colleague Gayatri Nair the key messages from this report that was launched earlier this year, Grid Codes for Renewable Power Systems. Today, you will find also the Chinese version available on our website. Feel free to download it for free. This report, contains the latest developments and to develop grid code connection code for power system with high share of variable renewables in like solar and wind. This is an update report from the report that was released previously in 2016, Scaling Up Variable Renewable Power, the Role of Grid Codes. It contains, as I mentioned, the grid code development, but also the technical requirements and their evolution of grid codes. Also puts into, brings on a chapter ancillary services and the relationship with grid codes. And then discuss the importance of regional grid codes and the importance of also having in place grid codes compliance procedures. And then finalizes with a short guidance for designing grid codes for policy makers. What we are trying to explore here is basically the role of grid codes and how they can support national energy transformation objectives in a very dynamic and innovative environment, and how public authorities need to provide very clear mandates to stakeholders to work together in developing these grid codes. We know that there are more type of grid codes like market codes, operation codes, but this report in specific, in particularly focuses on grid connection codes, which are the minimum technical requirement that generation plants and other assets need to meet to be granted grid access in a power system. We have 5 main key messages from this report, and we structure the presentation of today around these key messages. So we will see how grid codes should be technologically neutral and should evolve to meet system needs. The second key message is that grid codes should enable innovations to connect safely to the grid. Third, grid connection code requirements need to be tailored to country and system context. There is no recipe work for all and no silver bullet. The fourth one is regional grid connection codes is key to facilitate international power trades and ensure competitiveness. And last but not least, the fifth key message is an imperfect grid code is in many cases better than no grid code at all. So let's start with the first one. Grid codes should be technologically neutral and should evolve to meet system needs. First, it should evolve to meet system needs because the system needs are changing and power sector is changing. It's as also previous speakers have shown, it's becoming more decentralized, more digitalized, and with integration of high share of variable renewable energy, different challenges appear. This is a little bit of comparison of how the system is transforming from fuel source that used to be controllable, now it's variable. For synchronous machine to much more inverter-based resources, from large-scale power plants to more and more small-scale power plants, distributed generation connected to the consumer ends. Before, flexibility used to be provided mainly by the supply side, by generation. Now flexibility can and should be unlocked also from the demand side and via storage technologies that can be connected either in the grids or on the supply side or on the demand side. Now we're talking more and more about smart grids and digital technologies that are entering the power system, and also consumers are transitioning to being prosumers with installation of distributed energy resources. So in this case, the requirement of the system change over time and grid codes needs to be updated, and the cost of upgrades should not fall entirely on existing grid users, and the compromise should actually be reached on the burden of the cost. If the connection requirements applying to existing assets never change while the rules for new assets become stricter, the result will be a delay in replacement of old with newer, more advanced technology. On the other hand, if connection requirements evolve constantly for existing assets, huge investment certainly is created. Therefore, we want to emphasize that a balance needs to be struck between the two extremes. So this is a graph showing the role of grid codes in the transforming power system. We see that the decentralization and the digitalization and automation with the system requires more and more harmonization and interoperability, which can be ensured by new grid codes. Also, grid codes can prevent cyber attacks, which are more and more a threat in a more digitalized systems. Digitalization and also electrification and the use sector. So all these new small assets connected to the grid require new standards that can also be defined with grid codes. And grid codes can also enable new ancillary services that can be provided to the grid which would enable further the flexibility. So all these play a very interconnected role to enable high share of variable renewables in a changing system. Grid codes should specify the requirements in a technology-neutral manner as far as possible to help avoid the introduction of technical barriers for individual technologies and to allow to adopt the most economically efficient technical solution. I am pleased to introduce now to my colleague, Gayatri Nair, who would continue with the second key message. Gayatri, the word is yours.
Thank you, IRENA. I hope you can hear me well.
Yes, we hear you.
Thank you. So just to continue with what IRENA has been saying, one of the other key messages from the report is that the grid code should enable the devices to connect safely to the grid. So my presentation today will focus on how grid codes are evolving to include these new advancements that have been happening. And I'll also share some examples from countries who have taken the lead in integrating the other. So in this slide, you can see some of the basic requirements that used to be existing, or some of the existing requirements with respect to VRE plants. So the grid codes that have targeted VRE generators are usually to make them emulate the behavior of synchronous machines or to make them behave like synchronous machines. So the earliest requirements that were ever set were about voltage and frequency operating ranges, usually applied to all generators alike. Then regarding frequency control capability functionalities, there are requirements on over-frequency active power reduction and active power increase to provide inertial response or fast frequency response for a limited time period. And these are not mandatory as of yet, but it's coming into more prominence in the grid codes. Providing reactive power for voltage control, there are two aspects to that. One is the capability of a generator to provide reactive power, and the other is the capability to implement different control schemes. So that is again another requirement that has been seen in almost all transmission and sub-transmission grid codes, as well as in some distribution grid codes. Then controllability for active power and reactive power has been predominantly seen in transmission connected VRE systems enabled via SCADA system, where you can actually change the set points remotely. Fault behavior is another one, which is a common parameter, or variable that is being specified in some of the grid codes, and this ensures resilience to grid faults. Protection, so that the power plant is not overprotected. And then, of course, power quality requirements, so that strict limitations can be imposed on limiting the total harmonic distortion. And VRE generation forecasting is also becoming essential, as we can already see the example that was given by the previous speaker, that it is already there in China. Next slide, please. So, as discussed in the previous slide by IRENA, there is a very distinct way the power system is changing and how the power is being generated, distributed, and being consumed. So new technological innovations are being added to the power system, and there are new active participants in the system. So there is a distinction between the power generation and consumers are actually blurring. So there are new technologies, and whatever grid codes now come into effect should actually distinguish, should not distinguish between many individual asset types, but try to be specific or make technical specifications in a very technology neutral manner as far as possible. So this will actually help avoid introducing technical barriers for individual technologies and allow the users to adopt the most efficient, economically efficient or efficient technical solution to suit their needs and business cases. Next slide, please. So some of the trends that have been evolving and technical requirements that are evolving in the grid codes to allow a higher penetration of VRE or variable renewable sources are highlighted here. So those requirements of grid code specifications that were only applicable to larger users are now being extended to smaller users as well, so that they can actually connect to the system in a very system-friendly way, and they can also adopt or adapt the state-of-the-art technological developments and system needs. And one very notable case is the leveraging flexibility from small-scale grid users. Controllability requirements are being extended to rooftop solar PV and other small distributed energy resources. Then harmonization of communication interface, because now cybersecurity is becoming a very important aspect of our system security. Therefore, harmonization communication interface requirements are also being specified in some of the latest grid codes. Then low voltage write-through, which was usually specified for distributed resources connected to medium voltage or higher level, is now being specified for those connected low voltage distribution grids as well. Next slide, please. So controllability, so from the slide onwards, I'll try to highlight some of the examples. Some examples here regarding controllability is how, like I mentioned before, how power reduction or power increase capabilities can be made for newer additions to the system or active participants to the system. And mostly, this is usually specified to the extent possible without mandating an addition of energy storage. While VRE share is very low in the system, this active power management capabilities may not be needed, but this changes quickly as the share of VRE increases. So there is no downside to making this a requirement from the very beginning. So you can see the example. One is from Germany, where you have the PV facilities which are not connected to the grid. I mean, less than 30 kilowatt capacity needs to have a capable or limit their output by 70% if you're not connected and not controllable. Then regarding low voltage write-through, there, like I mentioned before, they were not mentioned for low voltage grids earlier, but now it's also coming up here. And one example, some of the grid codes that have actually cited this is the German grid code and the Japanese grid code. Then high voltage write-through, like the speaker earlier mentioned, there has been comparatively less emphasis on this in the grid codes, but now that is also coming up. Australia, China, and Spain have the most stringent regulations and have a grid code specification to withstand voltage rise of almost 130%. So this actually is to basically determine the performance of the generator during faults, and also specifies the tripping voltage threshold, clearing time, and it basically indicates how robust the system is with the distributed resources. Communication. So there are many different methods of communication and remote monitoring and control that can be implemented, but there is a necessity to have a single communication interface or a single type of communication interface, so that there is not much of a cost attributed to the different types there. And there are standardized interfaces that can be used in protocols that have been implemented. So in China, the communication at medium voltage level and system operators have to meet the relevant standards, including both remote monitoring and control signals. Next slide, please. Storage and other consumer producer connections almost are mentioned in most of the advanced grid codes, like Europe and United States. In the European network codes, they do not set any separate requirements for energy storage systems, but they approach it in a very simplified manner. So they consider storage to be the same as a power generation module. So they would meet the same requirements as a power generating module. But individually, some of the countries have developed their own, as has been highlighted in the slide here. EV charging, because of the increasing number of EVs coming onto the picture of electromobility, high charging power of each vehicle, and recent grid codes have adopted some requirements for EV charging as well. Because this is not a permanent storage, they have to in some of the grid codes, they are considered to fulfill the requirements applicable to generators while they are actually connected to the grid. Another aspect that is actually drawing a lot of attention, though they have not been specified in any grid code so far, is the grid forming inverters and that of black start. Now, grid forming inverters are a new type of inverters that will come into prominence more and more when the shares of VRE increases. And NSOE and the National Grid of Great Britain have actually taken some first steps to address this issue. And basically, they could specify the contribution of these grid forming inverters in maintaining synchronism and stability, and also to provide fast frequency responses during decline of the rate of change of frequency. Black start is an ancillary service that is also seeing a lot of rising importance when VREs replace the synchronous generators, which have been contributing to black start. So you would see that VREs can actually, now in the grid codes, the status is that they are usually part of the secondary resources after the re-energization of the grid or part of the grid is done. But with the increasing shares of VRE, they will also see a role in the or contributing to re-energization of the grid. Next slide, please, Arina. So another key message from this report is that the grid code should be system specific and tailored for the country context, which I feel is the most important message of all, because you cannot adopt grid codes from other countries because every system is individual and specific. So a technical connection requirement that you need to specify in the grid codes can be divided according to the issues that are to be addressed. High-level requirements are essential components of any grid connection code, while basic requirements may be very similar amongst all grid codes. There are significant variations possible in the chosen parameters and in the range of the grid user facility. So that will apply based on the country and the site or the power system specifications. So identifying the appropriate parameter for suitable user facility class according to system needs is a crucial part of the grid code design. Next slide, please. This is an indicative guideline of how requirements change with increasing shares of VRE. So starting phase, then the stepping up phase and the high VRE phase. Appropriate grid code requirements must be considered or parameters must be decided considering the generation mix, the size of the system and existing interconnection capacity. So this is not to match any particular system worldwide. This has basically been done by capturing the most common typical cases in developing countries. And systems with high shares of hydropower have not been covered in the report because their VRE adoption process is seen to be less challenging, and they have they already, they do not have existing fossil fuel based power plants to replace. So hydropower often provides flexibility to accommodate the VRE fluctuations. Grid code designers and policymakers aiming to facilitate VRE adoption can actually find similarities between the system and then adopt it for their own system specificities, and depending on the size of the system. Next slide, please. So this is again, like I think the speaker from CEPRI had already mentioned, there is grid codes always refer to these as product specification standards because it sets requirements and guidelines that are applicable to the design, installation, and commissioning of generating equipments and other equipments as well. And these all impact the way the grid codes are formulated, especially frequency, voltage ranges, for example. So they usually describe the behavior of the generating unit on the grid, not only at a high level, but and also they leave enough room to implement new functionalities. So if you take grid codes across the world globally, you'll find that these standards are always referenced in the grid codes. And when it comes to, especially when it comes to issues relating to unit design and power quality requirements. So this is a very non-exhaustive list. There are various other resources that you can actually attribute the grid codes to. So with this, I end my presentation and hand it over back to IRENA. Thank you.
Thank you, Gayatri, very much. Going further, the fourth key message is about regional grid connection codes that is key to facilitate international power trade and ensure competitiveness. Well, developing grid codes we know requires a lot of effort. So cooperation with others to share resources is often better, especially for small countries. The result will be improved market access for manufacturers of modern and advanced equipment, safer regional cooperation, and easier adoption of a high share of variable renewable energy resources in the end. Cooperation and coordination can go through different stages. Historically, regional cooperation and coordination was on matters related to power system security in emergency cases and was mostly organized through bilateral agreements. The nature of such cooperation evolved to bilateral trade of power to optimize net benefit. The shift towards open electricity markets, along with the introduction of increasing share of renewables, introduced a greater need for cross-border trading and TSOs coordination, which gave rise to the introduction of regional grid codes in some cases. For example, in Europe, and we will have later on NSOE presenting more in detail the European case. But basically, the European regional grid code requirements are minimum and non-exhaustive, which means that each TSO should specify additional and/or stricter requirements according to their own power systems. One of the key challenges in applying similar sets of requirements to all generators in the whole European Union is the fact that there are 5 synchronous systems of different sizes. So frequency stability functionalities may be required from smaller generators if the synchronous system is smaller, as each of the individual generator would have a higher impact on the overall system stability, which doesn't apply if the synchronous system it's bigger. Therefore, it differs. Regional connection network codes often focus heavily on ensuring operational security, but focus somehow less on actual harmonizing of technical requirements from what we have seen. And last but not least, the key message, the fifth key message, an imperfect grid code is in many cases better than no grid code at all. Especially, and this is valid, especially when economic conditions allow for renewable energy development to pick up pace. In this situation, the development of grid codes or a set of technical requirements to be imposed to generators is needed quickly. Such initial requirement can be developed based on international experience and good practices from countries of similar power system specificity, and may not be they may not be perfectly suited to the needs of the system, but they ensure certain minimum functionality of the new generators. And it is usually easier and cheaper to later reparameterize functionality to better reflect the needs of the actual need of the system. Requirements can be then evaluated and refined using more detailed power system studies, which would be repeated on a regular basis. Special care should be taken to not ask for excessive requirements that would turn into higher costs that could restrain the development of variable renewable energy sources. The implementation of these grid codes gives system operators confidence that assets connected to the system will not endanger the security of the electricity supply. Therefore, they're really important in opening up the power sector to private developers and new power plant operators and enabling efficient integration of distributed variable renewable generators. Just to mention, in the process of writing a grid code, it's important to install a working group with a very diverse set of stakeholders representatives from the very beginning, because no individual stakeholder has an in-depth knowledge of all relevant technical details. So involving all relevant stakeholders early on will shorten the feedback loops and would lead to a higher quality of a grid code. Grid codes also have a very important role in building trust between different actors. And I will end on this note. Thank you very much for listening. Here you can see also the cover of the Chinese version, and I would like to open the discussion and some remarks from experts about this work. I will give now the word to my colleague Huming.
好的，感谢 IRENA 和 Gayatri 的精彩报告。那么下面是报告。
Thank you very much. Next we go come to the comments.
Now we enter
may give the floor to
the
Mr. Xu Haijing.
discussions and commentary of the segment. Hello, thank you. Hello everyone, I'm Xu Haijing from the SGCC Department of the Research Department. I am very delighted to participate in the launch of the Chinese version of this report. First of all, on behalf of my department, I would like to congratulate the release of the Chinese version of the grid codes. Grid codes for renewable power systems is a timely and inspiring report. It is a professional guide for power science and technology researchers and practitioners. It is also an energy power policy guidance for policymakers and researchers. It is a popular science manual for interest readers as well. So generally, this report has both the breadth and depth for the profession, and it also takes into account of readability for the general public, contributing to its considerable value. I'd like to make 3 comments based on the SGCC's research, innovation, digitization, international standardization contributions. First, in terms of the technology development trends, this report orients to the 100% renewable energy scenario and summarizes the influence of the inverter-based power supply and safe and stable operation of the power system from multiple angles, including the grid forming, capacity inverters, inverter FRT, total systems inertia, and the role of grid forming inverters of the ancillary service network. Over the years, SGCC has carried out remarkable research for renewable energy and high integrated electric power systems. Second, we have also started the achievements of the digital transformation in countries around the world for challenges faced by digital transformation faced by renewable energies all over the world, and gave solutions from different scenario stages. The SGCC has made progress in the big data, cloud, IoT, mobile interconnection, blockchain, AI technologies, accelerate the upgrade of power grids to the internet, build a service ecosystem such as smart car networking platform and new energy cloud platform to help the digital transformation of core services of the grid power production management. Third, in terms of formulation and application of international standards, this report introduced the process of international and regional standards setting in detail, analyzed the mechanism of effective operation of standards, and listed the IEC and IEEE standard related to RE grid integration, serving as an important guidance for readers. The SGCC attaches great importance to the standard setting actively participates in international standard governance, strengthen cooperation with ISO and IRENA, especially leading the IEC SC 8A grid integration, renewable energy generation, technical subcommittee, which promotes integration of renewable technology and innovation. Finally, I'd like to wish the release of this guideline a complete success. Thank you.
国家调度中心主任
Next,
司
let's
教授
welcome
及
the Mr. Pei Zheyi to make comments from the Chinese version of the report. Mr. Pei Zheyi is Deputy Chief Engineer of the GCC Regional National Power Dispatch and Control Center. Thank you. I'm very glad to attend today's meeting. I've learned a lot. I'd like to say that this is a very timely launch of this report. We know that the climate right now has changed very drastically for the past few years, including floods that impacted our lives and people's livelihood. CO2 has also raised more than above multiple times compared to before the Industrial Revolution. There's also very rapid pace industrial development for many countries. Renewable development, including wind and solar PV, causes a lot of challenges and impact for traditional grids. This includes the issues of FRT, including the synchronous issues and protection issues. Once there is a high integration of RE into the grid, we have to consider, for instance, the amount of wind and the fluctuation of solar panels from day to night. So there's a lot of challenges in terms of protection, fluctuations, and storage. Right now for China, there is a lot of RE integration. We have also seen that with these renewable energy integration, there is a decrease in the resistance against fluctuations. This code grid allows us to look at the best practices and experiences from other countries. After reading the report, I think it is very detailed. It takes into account multiple regions and countries and their best practices and experiences. They're very typical and can serve as classical standard setting learning material. These experiences cover experiences from the Ireland grid, including subsynchronous and non-synchronous issues. There is a high penetration from 65 to 70% in Ireland. This is very high. Right now for China, the penetration has reached around 50%. There is also for inverter FRT for high voltage and low voltage. Right now, LVRT and HVR FRT faces a lot of these similar issues. And these issues are very comprehensive and covers a lot of grounds. These are all covered in this report. It also takes forward-looking statements and predictions, including for the ancillary service market, for system inertia, for other types of related technology and operation, taking into account new requirements for the grid. For this report, one of the most detailed descriptions is the guidelines and the interaction with the market, the power market. I think there is a closely linked interaction between these two factors. There is a comment that really touched my heart, which is that if you have a standard, I think it will be better than if you have no standard, because once you have a standard, you have a foundation to build on. The best case and studies here presented in the report summarizes the experiences from multiple areas and regions around the world. The report itself has also presented a guideline that makes it highly operable and learnable. I think moving forward, we need to look at technology innovation and look at how the grid can be adapted to meet new technologies that are surfacing by the day. We are also looking forward to more close international collaboration to learn and study from other countries and to spread China's best practices abroad. We also look forward to participate in international standard setting, including RE integration to the grid in large scale. I hope China can contribute more and learn more from the international stage. Thank you. Thank you, Mr. Pei.
有请中国电科院总工程师王伟胜博士进行点评。好，有请王总。
Next, may I give the floor to Dr. Wang Weisheng from CEPRI.
Webinar congratulations on the release of Chinese version of grid code for renewable power system. 有关这个报告呢，我想这个给我印象最深的是
for this report, I think there are 4 aspects which really impressed me. And you know, it released the importance of necessity of making the codes. Actually, just now, Mr. Pei said about this. It is not perfect, but it is better than nothing. You know, actually in China, we have the renewable energy law, which was issued back in 2006. And then we made the grid code for PV and wind back in 2005. But at that time, and actually, you know, I convened the compilation group. At that time, I found it was also actually imperfect at that time. Secondly, I think renewable energy dominated solar power system making of this code very complex. It is very challenging. You know, renewable energy will involve many manufacturers and developers. In our code, you consider the EVs, electric vehicles. So we need better coordination. We need to maintain neutrality in technology. And thirdly, also we consider the management complexity. We have this code and standards. And in our management, we also find the complexity as well. You know, in making the code, we consider a lot of aspects. Therefore, in maintaining conformity, it is also very challenging and difficult. I agree with you. Last but not least, what really impressed me is that I hope that in the future, we should have better international regional cooperation. So China in the last several years developed really fast in terms of PVs and wind. Therefore, wind installed capacity in China and the PV installed capacity in China has surpassed 300 gigawatt, and including some offshore wind, which is over 20 gigawatt. So in developing large-scale renewable energies and distributed wind energy, we have some best practices. So we hope that in the future, we can share with you our experiences in making your better codes better. Thank you. Thank you very much, Mr. Wang. Next, I give the floor to the Vice President of NCEPU, Vice President Bai Tianshu. Thank you very much, moderator. I'm from NCEPU. I am also in charge of a key lab on renewable energy, and also I'm a professor in electrification. I have listened very carefully to several reports. I found that today's webinar is very valuable. This code is very valuable. It also collected experiences of managers, operators, and other stakeholders of grid. So first of all, on behalf of NCEPU, may I extend my sincere congratulations to all of you. It is the fruit of the cooperation between actually the CEPRI and IRENA, I want to share with you my humble thoughts. First of all, actually, it is similar to yours. Coals are very important, particularly when China witnesses the fast development, the PV and the wind. It is more meaningful right now. Just like you said, the coals have set different roles for different units, and also the responsibilities of these units in different time period of operation. With the penetration of PV and wind increasing dramatically, and also the share of production increasing dramatically, power system will have more requirements for the boundaries of integrating them, including the voltage, frequencies, FRT, active support, etc. Actually, integrating these renewable energies have changes the roles of traditional units and generators. China is now making the thermal power more flexible, and I think that is very necessary for ensuring the system security and efficiency. Also, I find that the grid codes should looking forward into the future and should be stable as well. The codes should be made on the basis of future installation of wind and PV and their generation as well. Of course, we should have some perspective research that we can make the codes to lead the development of technologies, equipment, and also the whole industry as well. And also this code is very important for building a NTPS in China. And then it has analyzed the minimum technological requirements for integration of renewables. At the same time, it also have a prediction for the future technological requirements, as well as the need for auxiliary services. It also mentioned the distributed power sources, EVs, grid forming new energy generators, etc., and even storage. We find that not only technical requirements, but also cases. After translating it into Chinese version, it will help China to make its own technical standards for renewables and also for the whole system with high penetration of wind and PV. And thirdly, I find that developing new energy to solve the problem of climate change and global pollution is necessary. And this is common challenge for human beings and also common responsibilities. So I suggested that we should have stronger international cooperation, not only the cooperation with IRENA, but also with other countries through the platforms set by IRENA. In this cooperation, we can share our experiences, our best practices, particularly the cooperation on research. In this way, in the whole world, even we are in the different stages of integrating renewables, we can learn from each other and we can develop our renewables and a system in a better way with better technological progress. That's all for my humble opinion. Last but not least, I want to express my congratulations to you again. Universities are hubs of innovation. So in the future, in international cooperation, in joint research, we hope we can join you to make our due contribution. Thank you. Thank you, President B. And then we have high expectations towards the cooperation with you. Thank you. Next, I want to give the floor to IRENA. IRENA, the floor is yours.
Thank you very much, Huming, and everyone who expressed their intervention so far. Now, the last one, it's the senior operations specialist from ENTSO-E, Mr. Adrian Gonzalez. The word is yours.
Hello, thank you, Arina. Thank you for inviting me today, and especially for having developed this great report, and also for counting on ENTSO-E views when doing so. For technical experts, it is an excellent worldwide benchmark of the state of the art and allows better understanding on how the regulation is developed to tackle the challenges of the energy transition. For policymakers, it enables a better understanding of the power system needs and the solutions implemented in the different countries and regions. Overall, from ENTSO-E, we value greatly this accurate report. We use it as one of the main references for professionals entering in matters of technological and regulatory and cooperation matters, and also for divulgating learnings from the European case in other areas in the world that could benefit from it. I only want to congratulate IRENA and CEPRI for its translation and encourage to continue the dissemination.
Thank you very much, Adrian. And so he was a very important contributor to this report as well as reviewer. It's great to have you in this webinar as well and have your views. This concludes our first session of today on the report. Now we are heading towards the second session and to hear more technical presentation on experience for renewable energy integration in China and in Europe and around the world. So let me give back the word to my colleague Huming.
Thanks again to the expert from NTSO. Now we enter panel 2 and welcome the discussion from panel 2. And for this panel, we have a 12-minute session for each presenter. There will be an interaction after the end of each presentation. There will be a Q&A session following each presentation. If you have any question, please post it in the chat, in the question function. First, we welcome Professor Stabak, and his presentation will be on the flexibility for large-scale RE integration. Welcome.
Thank you, colleagues. Can you hear me?
Yes.
Okay, can I share the screen? Yeah. Can you see my screen?
Yes.
Okay, excellent. Thanks very much for the invite. Very pleased to contribute to this regarding this cost-effective integration of renewables. And we have been carrying out very significant amount of work in the UK specifically, but also in Europe. But one of the core aspects of this, I thought would be useful to emphasize the challenges associated, which is now already there are challenges in the UK, given again the specific position of the UK, which is island position, and also very large, nuclear power stations. So, and the system balancing with renewables is getting very big on the agenda. And the question is how we're going to make that work. I am going to present you some of the analysis which we also carried out with the government recently and our Committee on Climate Change. So this is to start with, to show you analysis showing that the flexibility is going to be a core relevance to enable cost-effective transition to low-carbon future. And what we have done in here is to look at, for example, you will see now in a minute, look at the extreme cases, what is the cost-effective decarbonization of the system. If you've got renewables, we've got to say CCS, but also nuclear and so forth. What is the right balance to maintain, to achieve the low carbon target while maintaining security supply as well? And what was interesting in here, that even you can just see in here, even when you can see in here that on the right hand side, wind, PV, wind, nuclear, and CCS. Just look at those those four technologies, and of course the cost of solar and PV and wind is less than half of the levelized cost of nuclear and CCS. But you can see in here what was interesting in here. This is again just to make sure this is a UK system, because this is the UK has got a big challenge associated with the system balancing, showing that if there is no flexibility, the model decided to build nuclear and CCS, not to build renewables. Although renewables were half of the price, because there'll be massive, more than 2.5 times will be curtailed, what won't be used. But now this in here, if we start increasing flexibility, this is just an example of using storage and flexible demand, that you can see that when we start increasing this flexibility, that the amount of renewables, which is solar and wind, yellow and green, is massively increasing, goes from nothing at all in here to more than 100 gigawatts of the overall wind and solar, by 2030, which is now big on 2035, which is big on the agenda. So you can see in here that when we got flexibility, you can see that, for example, the CCS disappeared immediately with a kind of say 20% of flexibility. Nuclear is reducing and renewables are increasing radically. And this is again what is one of the key aspects, is that to facilitate cost-effective transition of renewables, we would need to have flexibility in here. And you can see that this reduced, for example, increase 100 gigawatts of renewables, but there is still kind of nearly 10 gigawatts of nuclear, which is what the government is now putting on, because there is also issues around the firmness of the capacity of renewables, which is also an issue where and there are, as you may know, there are also big issues now around the kind of extreme events with a long duration of low wind and low solar, which is now getting big on Europe, and that's where the firm low carbon generation, but also where the, for example, where the hydrogen produced by renewables can be used to deal with those conditions. This is just to illustrate that the flexibility is going to play a major role. This is also to illustrate, when we look at this whole system cost of renewables, which is levelized cost plus system integration costs. And we've done analysis to show how do you compare in here, for example, renewables versus nuclear. This is just to illustrate, for example, that this is system integration cost of wind versus nuclear. So you can see if there is a small penetration of renewables, there is still a little bit of costs in here. Is kind of say 10 euros per megawatt hour in here, and that's all to do with the fact that given the conditions, which is what government is looking into, that potentially there would be, for example, there will be say a week when it's going to be very cold in the UK, there will be no wind, so we would need to have, and so we would need to have peaking plant to make that work. So therefore the capacity value is what this is, but the peaking plant is not that massively expensive. Now, if we when we increase the penetration level of renewable or wind in here, you can see if there is no flexibility, the system integration costs will increase significantly. But once we've got the flexibility, you can see that we can actually go to a very large proportion of wind and still be competitive against nuclear. And this is what is the important in here, that the whole system costs are critical in here for competitiveness. And this is something which is now getting on the agenda. And also there is still work to make the market design appropriate so that these flexibility resources would actually take part properly in facilitating integration of renewables. And this is something which is now getting. I'll mention to you some of the core aspects which have not yet been included anywhere in the world. So this is just to show you. This one is where this is. Sorry, this one in here. Yeah. This is the what is the value of flexibility. You can see in here savings. Annual cost savings, which is billion per year, by this is by kind of recent. We want to go above that, but let's suppose by 2030, You can see there are £8 billion per year savings if we have smart technologies such as demand side storage, flexible generation, and also smart control, which is getting on the agenda. And you can see on the right-hand side is in the middle is the core point is to shift from the historical approach when the security supply comes from redundancy in assets to move into the digitalized framework where the intelligence is doing this. And when we've got this control in place, you can now see where these benefits are. You can see the blue one is the operating costs, nearly £2 billion per year savings. There is also a reduction in reinforcement of distribution networks, which is this one, also reduction in transmission systems. But what is very interesting, hasn't been analyzed yet, is you can see the red one in here is the largest one, which is the reduction in investment in low carbon generation. So what this is demonstrating, this flexibility can enable us to meet the carbon target by building actually less renewables, such as nuclear and potentially also offshore wind, because we can make best use of these resources. We've got flexibility, so we can actually invest less, but to make it happen. And that is something which is critically important, again, for cost-effective integration of low carbon generation in the system. And that is something which is kind of getting a little bit is being recognized, although we still need to develop a framework which would recognize those values and enable access to some of these resources, revenues to these flexibility technologies such as storage and demand response and so forth, flexible generation, and so to make sure we are all doing the right thing. One of the core aspects which I want to mention here is you can see in here the change in costs. This is again UK case. Operation costs. This is to say that currently we are kind of energy costs are dominant feature. Ancillary services costs, are very small amount, and that's why this is not, it wasn't a big issue regarding ancillary services. But what was demonstrated here, that when we move to now a lower carbon system, that you can see that first of all, the energy production costs are going to halve in here by 2030, while ancillary services costs are going to increase more than 15 times. And this is again where the fundamental now design of appropriate markets, which would facilitate this cost-effective integration of renewables, is now getting more general. You can see in here that this is just the regarding frequency response, kind of the value in pounds per kilowatt. You can see that there is 2015, 2020. You can see there is increase kind of more than 10 times in value of frequency response, given again that we want to integrate cost effectively these low carbon sources, both nuclear and renewables. But renewables are in here the core aspect. And one of the obviously the big issues here is the reduction in system inertia, and that is also why there is now, and we will discuss it here already, significant value of these grid forming and following converters, which can help this, to make this system balancing much more cost effectively and reduce the overall requirements for frequency response and make this system work. So that is very big on the agenda. And just to give you a few examples regarding this analysis, which was again carried out in the UK regarding the transport sector electrification and how, and there is now big interest in the UK to have to have vehicles to provide some of these core balancing services. On the top right hand side, you can see you may be aware that, for example, London Transport London will electrify all buses and taxis by 2030 in London. And that would be, for example, just to give there will be 40 gigawatts of batteries, in buses and taxis. And of course, there will be additional one in vehicles, because now this is now decarbonization of transport is massive. And this is just to illustrate how important is, for example, controlling these vehicles in a smart way without compromising on service quality, so that drivers will have the full, we can carry out all the driving which they planned, This is just to show that if there is, this is just the two cases, but I'll just focus on this one. It is about what is the costs of charging of vehicles if you do that in a non-smart way. This about say £600 per year per vehicle. And if we do smart charging, which is that we will be charging vehicles overnight and all sorts of stuff, but without again compromise service quality, we are just charging them in different times because on what analysis demonstrated that on average vehicles are 90% stationary, which means that you've got a very significant flexibility as to when to charge them. So the cost will reduce. You can see more nearly 6 times. But if we do vehicle to grid, which is in here to do when we have a, for example, big outage of a conventional generator, we can actually inject power, say while vehicle is parked, only for 5 to 10 minutes to support balancing service. You can see in here that in broad terms, what is saying that the vehicles which provide this vehicle to grid, they should get paid for charging vehicle £885, which is, you can see, so you should be paid for charging your vehicle, because there is a massive implications on the cost reduction, and also you can see also in here that there is also negative emissions. If you go to full smart charging, it will actually reduce the overall emission of the system compared with if it's a non-smart charging, as to what are the carbon emissions. You can see that this business as usual is kind of nearly you can see grams of CO2, say 25. But if you've got a full smart, which is to do with vehicle to grid, you're actually negative. And that is why, again, we demonstrate in here that there should be significant benefits in here of doing that. And of course, if there is a massive other flexibility, then the benefits would be reduced. But it's still significant in terms of the vehicles should get paid for drivers should get paid for charging vehicles if they provide these vehicle to grid services. This is again to show regarding the importance of synthetic inertia of if the wind plants can provide inertia, how that would change the overall cost. You can see in here, given the amount of wind going forward, you can see that if we do not have these forming converters and we just have a no static inertia, that you can see that the cost in the UK, this is 60 gigawatts, would go from say 300 million to 3 billion in here, more than 10 times in next 8 years. But if synthetic inertia can be provided by wind generation, you can see that there is a massive benefits, reduction in costs, significant if the renewables, wind in here, can provide inertia, for the system. Given that this is where the big issue is, because currently we're going to have huge amounts of renewables and also large-scale nuclear, as I mentioned, in which case the system management is massively important. I will drop this one. This is again to show that there is a massive interest in Europe, in Northern Europe, regarding the integration of offshore wind. There is currently proposition to have, more than 400 gigawatts of offshore wind in the North Sea. And the question is that in here showing that if we do kind of just connecting individual offshore wind farms to the shore versus having integrated approach, when you actually connect the offshore wind and also interconnectors, there will be massive benefits. You can see nearly, more than 50 billion pounds in here benefits if we've got a proper integration of renewables. And that's something which is also now getting been on the agenda. There is also, which we have carried out, with regarding having a pro-European wide approach versus member state-centric approach, and how this would potentially reduce the overall cost. You can see in here that if we had a for capacity markets proper in Europe, there will be 70 billion euros savings by 2030. Also balancing market, because currently interconnectors is fundamentally used only for energy transport, but would also, if we can increase the balancing market between the areas, that would also massively benefit. And also, if we coordinate deployment of renewables, respecting the physics that north of Europe is windy and south is sunny, that would bring massive benefits if there was a coordination of this, which is also important for system integration. Also, there is now quite a big interest, and also in China, there was a big development and also very significant progress in development of new transmission technologies running at more than 1 million volts, which can actually link in here, just to show, we can link in here, say, European side can link, Africa and also Middle East, and that would potentially make massive benefits. But still, again, we need, in terms of this super grid, we need to have a, proper policy framework. And also that is also potentially be applicable in China, given the, again, linking north and south in a much more strong way, which could provide massive benefits going forward. This is just to illustrate also, just to say that there is also significant importance of coordinating different energy vectors. This is just to illustrate an example. And again, the UK, if we've got district heating systems, which is showing in here that, if we negative means we invest more than what would we do if we ignore the system requirements. It's just to show there will be benefits of actually having some thermal storage in district heating systems. The benefits in here will be massive in terms of, regarding the low carbon generation, also OPEX and CAPEX and so forth. This is again showing that would, regarding the integration of wind, that this would integration would enable us to have much more wind and less from low carbon generation to make that work. And that's again where we need to have the integrated approach between electricity and other sectors properly. Also, this is just to kind of highlight that, also storage, for example, demonstrating that the multi-energy system coupling is going to play a major role. So we need to link heat, transport, electricity industry, just to show that this is showing that, for example, if you got a thermal storage, that you would need potentially much less of the electricity storage, and this is where the regulatory framework needs to develop. And just to highlight the historical approach of the market, which is what we had in the past electricity. We got TSOs and DSOs, the retail market. Given that we are going forward with all of these topics which are driving this climate change, security technology, and so forth, that we need to link in here all the energy sectors together with the electricity, and also have the interactions between local district areas and national level, because this is where the big flexibility comes from the demand side. And this is something which is showing that we need to massively change the market specifically to make that work. And this is where the whole system approach is required. And also one of the important aspects is to shift from the incremental approach to strategic thinking, because we need to, when we talk about decarbonization, we need to think about, where we're going to go in the next, few decades, and make the right decision now to make sure we are following the cost-effective transition. Thank you very much indeed.
好，感谢 Stebak 教授。刚刚呢 ，Stebak 教授从大规模可再生能源并网后所需要的灵活性资源出发。
Professor Strobeck just discussed the flexible resource needed for large-scale RE integration and flexible analyzed market scales, effect of RE integration costs and market. Thank you again. Because of the time, we will have no time for interaction and Q&A for this segment. Next, we welcome DII, the president of DII, Paul Vanson. His topic today will be integration of net zero emission energy carriers in the global energy market. Please welcome.
Thank you very much. I will share the screen.
谢谢。
Let me see. So thank you very much. Can you hear me? Thank you, CEPRI and IRENA, for outstanding report, and also the speakers before me, in particular Gordon Storberts, who actually more or less explained exactly what I also wanted to tell, the importance of an integrated approach. If you look at the world, then we have different power and energy systems in the world, but they all are coming bottom up and local, from a local basis, and there are of course interconnections at the power grid side, and there is an international and global energy market. But we have to all, at the end of the day, the same objectives of net zero emissions, energy security and reliability of supply, and also lowest cost. And we come from different sides, but have to try to get this job done in the most effective way. So this means cooperation, connecting, and also building a global market, not only on the say the area of fuels and gases and coal and so on, but also on the level of power systems. If we look at the electrical power systems are of course pivotal, and we see this in any places and countries. But power systems are only like a part of the total energy supply. I think that electricity energy is about 20 to 25% of total energy consumption of the world, which is about like 150,000 terawatt hours. So when we integrate the markets of so-called electrons or power and molecules, like we know them from fuels and liquid and gases, then of course the first priority is access to clean and reliable energy, but also no wasting of energy, and also using the demand side as a flexible matter, and not like a holy cow that only consumes. And that's also what the previous speaker was pointing about, the high importance of flexibility. Then local renewable energy for local use and connected to the power grids is of increased importance, especially if you want to go to, in the end of the day, to a net zero emission system. For that reason, we can expect more energy security, because renewables is one of the most secure sources on the in total. Not momentary, or not at each moment, but in total. Controllability is very important in renewables. We have seen this also in the previous speeches. Low losses and low cost is what is needed. As we need to push for renewables, it is very important that the renewables get a sort of premium in the market. And that is something I want to highlight in this presentation, the fact that we need to push renewables from a market point of view. Emission reduction, as you know, is a global issue. So it's important that that we know where carbon emissions take place, in what corner of the world, because they have the same effect to all of us, to the whole global society. So it is very important to build systems in which we have penalties for emissions, net emissions. And then the fourth point in the priority is actually this international optimization, which can be reached by a global energy trade, connecting emission-free sources with demand centers, and in an optimal way. The previous speaker has shown the example of the North Sea, in which all the North Sea countries are building a connected system that can optimize the sources, the wind and solar and hydro, with the demand side. So global trade of electrons, so power, but also molecules like gases and liquids and solids is important standardization, and also a way to to give this a value in the market through green and emission certificates. So if we look at the energy transition at the global level, then we need leadership in these different priorities. Net zero, the most important thing, of course, is phasing out harmful emissions along the value chain. So we have to accumulate renewables and economic nuclears in the grids. And also, if there is still fossil or carbon available or used in energy systems, then they must bottom line become net zero. So that can be done by carbon capturing or recycling of carbon, so that in the end of the day, this carbon does not stay in the atmosphere. About lowest cost of production and affordable supply to end consumers, it's important that we give priority or look for priority for the cheapest and fastest technologies and also the best locations, locally and globally. So we have to look more and more at the global level, like where are the best locations where we can apply the fastest and the cheapest technologies like PV, for instance, or wind, or solar, or hydro, geothermal, and so on and so forth. Then it's also important that we swiftly reach economy of scale of net zero power molecule energy carriers. So economy of scale in the sense of hydrogen, if we use hydrogen will be introduced as a net zero power molecule in the market, so that we take care that it can reach its economy of scale as fast as possible. Then also, is it very important that we use the markets, or as much as we can, the existing infrastructure at the power systems, but also the molecule systems that we have, like the oil and gas industry, that we use this for net zero energy carriers. We see also in that sense a trend toward DC systems and also hydrogen. Then, of course, connecting cheapest sources with end consumers by trading interregionally and also at the end of the day globally. And then another cost reduction issue is shifting, for instance, energy intensive demand to the renewable sources. Like if the present moment energy intensive demands is sitting somewhere where there is not really, are no really major renewable sources, then the question is, where could they move to? Security of supply, of course, full use of reliable emission-free sources locally and remotely, facilitating less dispatchable renewables in the grid. We have seen a lot on this in the report of CEPRI and IRENA, creating jobs and industries, in particular close to renewable sources. This is, of course, very important also to give incentives to the parties. Transparency, integrity, market liquidity, and fair price discovery is very important in this concept. Then, actually, the message for my presentation is more that we should build a market in which we can separate the physical parts, the electrons and the molecules, from their property, green or net emission free. And that can be done through certificates, so green certificates or guarantees of origin and emission credits. And these two, the physical parts and the certificates, should be traded in separate markets. The physical markets are already existing today, so they can be expanded, and together with the grid codes should be facilitated. And on top of this, we would then get our markets for trading certificates, which would then also give a market value to green and to net zero. And I can show this in this picture. if you look at the left side, in worldwide, we have only 3 types of energy sources in this concept. In this context, it is the fossil-based energy sources that have the problems where we have to solve these problems at the fossil level by capturing carbon. The other source is renewable, and IRENA is a great supporter, and together with the world community, we all push for renewables, which in the end could become 100% of the total energy supply worldwide. But we have also the option of nuclear. Nuclear is still a real option that we see in the different continents. Then these 3 sources produce physical energy, and this physical energy has no color because the electrons and the molecules do not know, and you cannot identify in the electrons and the molecules how they have been produced. So these molecules and electrons are traded in their own markets. That's the power market, the gas market, hydrogen, methane, liquids like ammonia or methanol or kerosene or solids. And in parallel, we need the information that for each molecule or each electron, we have some measure of energy emission reduction. And that can be shown through a certificate that at some place on Earth, in any case, the emission from, or the fossil emission that would take place by burning fossil will be captured and stored or will be recycled. The other certificate is the certificate that shows that an electron has been produced by a renewable source. And this energy, this electrical energy can then be, or it can then be expressed in a certificate, but can be traded in the market. In the marketplace then will be a physical market that we know today already, and on top of that, worldwide, so not only in Europe or in the United States or in China, but in the whole world, that we have can exchange these certificates. It's emission-based certificates and green guarantee of origin certificates, green certificates. And then at the demand side, which is the most important in this context, that this flexible demand, there will be 2 cost issues, 2 cost items: the physical price of energy, and then on top of that, a premium for emission, so reducing the emission, and the premium, and/or a premium for the green guarantees of origin. So this would be the picture, in the end of the day, the ideal picture to move the energy transition on a market basis. So at the end, also a little bit because of time restrictions, I have to keep it very limited to at least these measures of building together an international market for physical electrons and molecules, also facilitated, and the virtual. Thank you very much.
Thank you, Mr. Benson. He introduced the long-term transition goal for each continent and the long-term goal and benchmark for energy transition. So thank you, Mr. Benson, for your report. Are there any questions right now? Because of the time, because we are running a little bit behind, let's skip the question.
So, Rita, the floor is yours.
Thank you, Huming. Well, with no further ado, I'm happy to give the word to our next speaker, Mr. Adrian Gonzalez, Senior Operations Specialist at ENTSO-E. He will be talking about European grid codes, connection network codes, overview and evolution.
Thank you very much, Arina. I hope you can see my slides.
Almost. It's yes. Yes.
Thank you very much. Thank you again for having me. Without further introduction, I will jump into the content due to the time. So a bit of overview. I am part of ENTSO-E, the European Network of Transmission System Operators for Electricity. We are the organization for the coordination of 39 TSOs in Europe, acting as a common voice in front of the stakeholders, as regulators, policymakers, industry, and society in general. We as operators of the backbone of the energy system are responsible of leading and implementing the energy transition in Europe. And so it was created 13 years ago and was given a mandate from the European Union to develop grid codes at a European level, the so-called network codes, with three main goals: ensuring the security of supply, create a competitive pan-European electricity market, and decarbonize the electricity sector. The network codes were then started to be drafted by ENTSO-E, covering three areas: connection, operation, and market, with the codes and guidelines that you can see in the slide. After some years of drafting, taking into consideration the diverse system needs across Europe, the views of the stakeholders, and the approval process at regional and national level, the network codes and guidelines became European law in 2017 and have been implemented during these last years. In this slide, you can find an overview of the different regulations that are in place in the power system in Europe nowadays. As European Master Rulebook, enforceable in all member states, we have the network codes and guidelines, which tackle all the matters with cross-border impact. In addition, the national grid codes establish the ad hoc regulations in each state, while others, as the implementation guide and documents, give exhaustive but non-binding technical recommendations on how the network codes shall be applied. Talking explicitly about the connection network codes, they provide a harmonized baseline for the national connection rules. Among its multiple benefits, this approach promotes stable pan-European operation, robustness of the system, efficiency in electricity market, and overall sustainability of the connection requirements over equipment life cycles. As displayed before, we have three connection grid codes: the requirements for generators, the demand connection, and the HVDC network code, establishing the capabilities and behaviors for the different kind of assets and grid users in the field summarized here. I won't enter into the detail now because of the lack of time. But being proud of the benefits that the network codes have brought to the European electrical system, ENTSO-E is conscious of the need of their constant update. From the innovation studies, forecasts, network development plans, and analysis of incoming challenges, we have produced numerous reports, position papers, and recommendations in the recent years. By doing so, we have prepared in these last years an ambitious set of amendment proposals for the connection network codes to update them to the challenge of the coming decades. Recently, the European Commission and the regulators, ACER, the Agency of Cooperation of Energy Regulators in Europe, have launched the process for amending the requirements for generators and the demand connection codes. So we are now intensifying our coordination with them and the industrial associations, as we need to ensure an effective update of the regulation as soon as possible. As some of the experts have already mentioned today, the massive renewable development, the storage, the power to gas, smart grids, and demand response are examples of areas where regulation shall be improved, with concepts as grid forming capabilities or enhanced or oscillation damping being our daily work for these amendment proposals. When doing this, we should not compromise legal certainty, avoiding the retroactive applicability of new requirements, which is especially challenging in the rapid changing context we have nowadays in Europe. The very high electricity prices are promoting a quicker energy transition, so grid costs shall evolve as fast as possible to keep the lights on. I remain open now to your questions. Thank you very much for your attention.
Thank you very much, Adrian, for the very insightful presentation of ENTSO-E and the network grid codes in Europe. I'm not sure if we have any questions in the chat. Maybe we keep the questions for the very end if some questions emerge. Meanwhile, I give the word back to Huming.
Thank you, IRENA. I'd like to invite Professor Xie Xiaorong from Tsinghua University. Professor Xie's speech will be sub-super synchronous oscillation problems, hypervision of renewable energy integration. Please welcome.
Hello, can you see my screen? Okay. Hello, my name is Xiaorong Xie. Thank you for joining this event. I will talk about super-synchronous control interaction, or SSCI, in renewable power system. A majority of this content in this presentation is based on IEC joint work group on the system issues regarding integration of wind and PV generation into bulk electric grid. This work group is led by Mr. Yongling Chi. I was coordinator of task number 2. So it is a joint effort made by many Chinese and international experts. The presentation will cover the following things. First section introduces the new stability issues in renewable power system. The figure shows the conceptual next generation power system with higher penetration of renewables on the generation, distribution, and the utilization side. Diversified renewables and power electronic equipments with different control strategies are significantly changing the dynamic behavior of the system, previously dominated by traditional synchronous machines, and bring new security and stability problems. The power system stability issues was defined and classified by IEEE CEPRI Joint Work Group in 2004. It has 3 basic categories, namely rotor angle stability, voltage stability, frequency stability. However, from the perspective of converter-based renewable generators with multiple timescale dynamics, the emerging stability issues can hardly fit into the existing classifications. In 2020, IEEE PS working group proposed a new classification by extending the classic one of 2004. On the right side, 2 main branches were added. The first branch is the converter-driven stability, and the second branch is the resonance stability here. We have also classified stability of new power system from a different perspective. In this figure, the power system stability is broadly divided into fundamental component stability and non-fundamental component stability. By fundamental component stability, we mean the ability to maintain the stable operation around the nominal frequency, that is 50 or 60 Hertz for the AC and 0 Hertz for DC system. The non-fundamental component stability is the system's ability to avoid or resist the unwanted non-fundamental electromagnetic oscillation components. It is further divided based on the frequency range, for instance, into the supersynchronous and intermediate frequency and high frequency oscillations. Yeah, the IEC technical report on SSCI focuses on the super and supersynchronous oscillation. Let's have a look at the SSC events in real-world power systems. For more than a decade, power systems around the world are experiencing emergency wideband electromagnetic oscillation in convert-dominated power system with frequency ranging from a few hertz to more than 1,000 hertz. For instance, subsynchronous oscillations, supersynchronous oscillations, higher frequency oscillations, which can be collectively called as wideband oscillation. We use the term SSCI to describe the interaction. The SSO is the oscillation resulting from such interaction. The timeline in the figure shows several well-known SSCI events. For instance, the SSCI events in the Accord system, and the SSCI events in the Guyane system, China, and the SSCI events in the Harmi, Xinjiang autonomous region. As shown in this figure, more SSCI events and wideband oscillation events have been reported around the world. The oscillation causes damage or disconnection of renewable energy units, torsional cracking of steam turbine shafts, and even global stability accidents. A lot of research have been done in this area, resulting including that converter control actively participates in the SSCI. The magnitude and the frequency of the oscillation is determined by system-wide factors, including a number of in-service units, output power level, grid strength, or control structure and control parameters. What's more, the magnitude and the frequency are time varying around the events. Then I will briefly overview the modern analysis approaches for investigating the SSCI. In the time domain, there are three widely used methods for SS studies, namely the state space modeling and mode analysis, the nonlinear EMT software simulation, and the control hardware in the loop tests. Recently, frequency domain impedance-based methods are gaining popularity. The impedance model of individual components can be developed in DQ or sequence domain through mathematical derivation or perturbation-based measurements. At the system level, there are different ways to represent the impedance. One is the source node modeling, where the impedance model of the whole system can be obtained by dividing it into source and load subsystems. The other is the impedance network modeling, which preserves the detailed network structure as well as oscillation paths. To judge the system stability, many methods are proposed, for instance, Nyquist continuum and the reactance frequency crossover method. Then it's necessary to take appropriate countermeasures to mitigate the risk of SSCI. There are 4 stages where appropriate action could be taken, namely planning, control, protection, and operation. In each stage, the countermeasures could be fulfilled on the grid side as well as on the general side. This table lists some of the measures. You know, this is a research area of rapid development. New methods are constantly emerging. This is an example of grid-side subsynchronous damping controller. It adds positive resistance at the target oscillation frequency. A customized shunt converter is used to inject the subsynchronous currents into the grid. A 10 megawatt prototype has been developed and installed at the Chabe substation in Guyane wind power system to dampen the oscillation. The effectiveness was verified through experiments. In the same system, generator or roadside damping control are also demonstrated. Supplementary control loops are added to the wind generator's roadside converters to improve the stability. The damping performance with and without the control function is validated through the hardware in the loop tests as well as field tests. In another practical system, that is the Jiangbei Mijago wind farm, the general site damage control proved its effectiveness again. In this case, the wind power is transferred through the voltage source converter-based HVDC transmissions. At the end, I want to discuss further development on the grid codes related to the SSCI or other stability issues. In China, a recent grid standard, namely Guide on the Security and Stability of Power System, covers the oscillator stability issues. It is required that wind and PV power plants with wideband oscillation risk should take in corresponding warning and separation measures. There are also efforts established by the State Grid Corporation of China to establish and maintain the library of impedance responses of inverter-based resources from various manufacturers. Globally, there are efforts by utilities and system operators to accommodate SSI stability requirements into grid codes. Meanwhile, many working groups or task forces have done some work towards this purpose. For instance, the IEEE IEC CEPRI work groups and task force associated with SSCI and SSO, in which many researchers, including myself, have joined during the past years. However, collaborative efforts are needed to establish grid codes, standards, specifications, and guidelines. This is very important because manufacturers of IBRs are international vendors. Some unified interfaces are required to connect their products to the different grids. To conclude my presentation, I would like to make a brief comparison between existing classical low-frequency oscillation, subsynchronous resonance, and the emergency SSI issues. There are standard benchmark models, PSS, recommended practices, design and performance criteria, and so on for studying the classical stability issues. However, there are almost no benchmark models, recommended practice design, and performance criteria for the emerging SSI stabilities. This indicates a gap which we can jointly make efforts in the future. So, okay, that's my talk. Thank you again for your attention.
Thank you, Professor Xie. Professor Xie has introduced us the concept of a stabilized net and grid, and he has also introduced us other concepts. So thank you, Professor Xie. Are there any questions for Professor Xie?
So thank you again without any questions. So last but not least, I may give the floor to our guest from Nestor, the CEO of Nestor, Mr. Silva. His topic is renewables integration, integrate and support to the system operation. The floor is yours.
Hello, good morning, everybody. Hope you are all listening me well. First of all, I would just like to thank for the invitation to be present here and to share with you our input to this topic, and also to congratulate not only IRENA but also CEPRI for not only for the reports but also for putting up this event and this sharing of information. I hope you are all seeing my screen correctly, right?
Okay. Yes, we can.
Yeah, very good. Yeah, so just a quick pair of words on ourselves and our work. So we, as a research and innovation center based here in Europe, we look into several topics related with energy transition. As you can see here in the screen, going from topics of integration of renewables, digitalization, markets, asset management, simulation planning. Well, a set of all different elements which are being impacted by the energy transition, and all these in the context of the sustainable objectives of the United Nations. And we do this in a mix between innovation and research and development on one side, and on the other side related with the real system and network operation because of our deep connection with operating entities and operators throughout the world. So in this sense, our idea is to provide innovative solutions with new tools, strategies and processes that are well tuned to the new energy paradigm and serving as a driving force towards more efficient and sustainable energy systems. And so having said this, today I wanted to, due to time restrictions, to focus on two particular topics related with inertia and ancillary services before summing up with a few takeaways related to this, because the topic is very vast and we could address it from a lot of different angles, but I decided to pick these two to show you also the work that we have been doing regarding this topic and how we see this going forward. And so just a quick message, of course, to say that the energy transition is of course associated with a changing mix of generation. As you see on the top left imagery, the change from very masses of inertia in the system, giving room to different distributed resources generating or consuming as storage, but mostly generating as wind and solar. On the right-hand side, some imagery that shows you that we are moving also from more mechanical devices to electronics in the system. And also in the bottom center, you can see the increase in the number of inverters that populate the energy system, or in particular the electricity system. And of course, this energy transition impacts, of course, the inertia on the system frequency. And with the increase of the integration of inverter-based resources coming from this wind, solar, battery, but also with EVs as well, there could be periods when the total inertia in the system is very low, as we have been discussing before, with less synchronous machines being able to be dispatched. And so we see the rate of change of frequency increasing, and so going from 0.5 to 1, as we see here in the graph. And so we see that there is less inertia in the system, which is and was expected. And so one important thing is to be able, and also from the system operation point of view, to monitor with more accuracy and with more continuity the hours of low inertia, and understand something that in the past was very stable during a long period of time. And so from the system operator, this was not necessarily a critical issue. And so looking at inertia, not only from a single machine point of view, but also from an integrated system and from a power system as well. And so if we look here into this monitoring, this information regarding the, in 2019, the kinetic energy in Central Europe, you see on the left side, that, well, of course, there was some fluctuations, but there was a strong basis, as you see there with the blue in the bottom, associated with the nuclear in France. And then, of course, also some other more stable assets as well in terms of providing kinetic energy, of course, with several fluctuations already occurring. And then on the right side, you see that throughout the day in the vertical axis and throughout the months along the year in the horizontal axis, you see some stability there, of course, some darker regions as well. And as we see for a scenario for 2030, we envisage, in particular, if you look to the right graph, that the level of inertia, as measured by the metric that I mentioned before, that I showed before, going down in terms of value, and so going darker in terms of the imagery in the graphic. On the left side, you can see this represented in another way, which is it's an histogram of the number of hours of the year, in which the number of GVAs is providing kinetic energy. And so the blue line on top is the one we had before on 2019, and all the other ones very much below are different scenarios for 2030 and 2040, DG being the distributed generation scenario, which is the one which is more considered to be the more realistic at the moment. But you see that there is an increase in the number of hours in which the number of GVAs is very low. And so this shows us that the energy transition is in fact happening, and we can see it very clearly in these graphics. Also here, this is in Portugal, a result of one of our previous works, looking from 2010 to 2019. We have checked all those 10 years, and we have seen these graphics evolving, as you see there from the left to the right, in which on the left axis you have the number of megawatts, in particular in Portugal, not anymore at an European level. And so on the left axis you see the number of megawatts, and on the right axis you see the percentage as compared to the generator level. And you see that this is the blue lines and the green lights are going down, so approaching the threshold that was set here in Portugal for 2000 megawatts in terms of inertia for being something comfortable, and not going down the 40% if you look at in the percentage side. And you see that in 2019 energy transition was happening via inertia here, with the number of megawatts going below 2000 in several hours, and also below 40% in a lot of them. You can see this also through these histograms. On the left, 2010, you see the lines much higher, and as we progress to 2019, you see them coming down, and towards the end of the graphic, the last tail on the right side, you see that the number of hours in which percentage is below 40%, and in which the number of megawatts providing inertia is below 2000 is rapidly increasing. And so this is just to make evident and how we can see this in a very tangible way. And of course, this requires for more accurate and continuous estimation methods. And as you know, based on our work that we do in CEPRI and in other fora, several ways of measuring this inertia, depending on the data that we have, whether it is real time or if it is offline data, and what type of devices you use to measure this. This is increasingly a hot topic high in the agenda, that different operators should take a look in this and check what is the best way. In particular, a recent one, this is a work from last month, presented by Airgrid, the TSO in Ireland, in which they have came up with this another metric, which is the system non-synchronous penetration. In fact, they have been using this for a long time, but basically these measures, as you can see there in the formula, not only the renewable components or the stronger renewable components of wind and solar against the total system, but also including the HVDC imports due to their characteristics regarding inertia. And you see that the idea was to have them, this number SNSP below 50%, and then coming to 75, it would be more dangerous. But last month they updated this and they say they are comfortable already with 75, and in fact they are already operating in 75, which shows that system operators are adapting to this transition, and also as the report from IRENA mentions also, there is increased confidence in terms of managing the system with renewables, and operators are being able to cope with this. Other countries are also looking into another metrics to measure this, like this one in the UK, the Samuel inertia element, in which they use the bid market units to estimate the system inertia. But just to show that there is an increased concern on how to measure this and to make sure that it is continuously controlled. This brings us to another topic, which was mentioned also in the previous presentation regarding oscillations, which is the assessment of what is the amplitude of these oscillations, and in particular, the maximum amplitude happens in peripheral countries, in the extremities of the system. And since Portugal is the most western country in the continental Europe, our observations there are very relevant, and in particular, the Portuguese TSO using PMUs since 2010 to have a continuous monitoring on these. And as you can see there also in the graphs on the mode shape there, the oscillations in Portugal and in Iberia much stronger than the other ones in Central and Continental Europe. In particular, with this incident that happened 2 years ago in September 2020, when one of the lines between Spain and France went out of operation, and so there was a big impact and flows exporting or reducing the export from the Iberian Peninsula. Of course, the Spanish operator was able to change the HVDC tie line modes to damp the oscillations, and so this is controlled. But in a way, it shows also what I wanted to show here in this graph, the importance of coordinated analysis on a more regional and global level. In fact, we are providing all this information, in particular to Switzerland. The TSO from Switzerland is collecting all this data and allows an integrated view and an integrated understanding of what is happening throughout Europe. And you can see that in the left side graphic, the red line, the one oscillating more, is the Portuguese one, which is the one in Ricarei, basically the PMU that we have there, and shows a strong oscillation there. That is also noticeable in the top right graphic with the blue line, which is also the Portuguese system situation. And you know, this, as it was mentioned before, these severe frequency events are increasingly frequent in Europe. You have here several examples that have been occurring, and as you know, it's the responsibility of the TSO to detect in real time this type of phenomena in his control area and to act in time to prevent any cascading implications. And so this brings also the interest, another topic I wanted to include in here, which is the need to review the definition of the WAMS settings. And so in these oscillations, east, west, and north, south, it is important to have an updated histogram of the oscillation frequencies that occur. And so to understand what are the frequency modes that should be triggered, or which are the alarms in which frequency modes that should be triggered. And so that's another exercise that we have done, and it is important to continue doing this, which is based on the current limits and the proposed limits in view of what is being observed. And so based on our work, we have been able to update a lot of mode settings in terms of having alarms to detect when to actuate in different situations. So this brings implications to the system operator. And so this is the point of my presentation, as well as implications to the operation, which is continuously monitoring and analyzing inertia. Is it declining or not? The rate of change of frequency, the mitigation schemes, the reserves. And so there is a process that needs to be designed and needs to be periodically reassessed, as it is mentioned there in the text on the right side. But moving quickly to the second and last point of my presentation, which is coming to the ancillary services that are needed for this energy transition. And so looking in particular into frequency control and voltage control. And so, as you know, the motivation is very clear. I think the audience already understands this, that with the very high penetration of renewables, this requires a primary frequency control. Until now, it was mostly relied upon synchronous generation. The experience with non-synchronous machines was low until very recently. And so there is a need to increase the confidence with the renewables providing this service. And this is what we have done. And so we have tested this. And in particular, we have looked into wind to be able to provide frequency control. Let me go quickly through this, which is situation in which we have some reserve and some deloading of 5%. But of course, the wind generators do not like this because they might lose revenue. So we looked at, into other situations, which is inertia emulating. And so taking use of the rotating blades having inertia. And so to be able to change the pitch of the blades, and with that, making some modifications in the contribution of the wind turbine to increase the active power, in particular in the first critical 10 seconds, and that worked. And it could be done with a constant set point that was set for the wind farm to follow, or also with the variable set point, which was also successful, and we managed to see the wind farm following the set points being provided, not in a constant form, but in a variable form. Then another aspect also is voltage control, okay? And voltage control here, we looked into the voltage droop control, in particular with wind, and making sure that the tangent phi was below 20%, so minus 0.2, and we managed to see that the compliance with this tangent phi requirement was confirmed. And so also in the PQ diagram that was clearly observed with the data points there showing the operating mode inside the operating boundaries. And also for the voltage droop control, we could see that our test points and our data points from the field all fall into the lines that were expected. And so this is a real evidence, and gaining confidence with the renewable energy service sources providing these services is what this shows, yes, and this is important. By the solar side as well, the ability for solar also to provide voltage control. We have done that, and so we have here a single line diagram of tests performed and the inverter power control diagram that was used. And so all this power control is critical in order to ensure that solar power plants can in fact provide voltage control. And we could see that the voltage was able to react to the changes that happened, first without droop control, as you can see in the first half of the graphic, in which everything is constant in the reactive power there, and then in the second half of the graphic where we introduced droop control, and you see that the reaction is opposed to the green and to the blue line. You see that also in the oscilloscope in the top without the voltage droop control, and in the bottom with the voltage droop control, showing that the inverter adjusted the reactive power to compensate voltage deviation. And we can see that also with the KU graphics as well, and showing that the data points collected from the field in fact shows the ability for these renewable energy sources to provide that information. Final two slides, just to say that these ancillary services also need development in this energy transition. I think it was mentioned before in the intervention also of Professor Gordon Stravach that the value of the ancillary services is going to increase because they provide the flexibility that is needed now in the system. The emergence of new services, as you can see here, also from European TSO as well. A lot of new services coming up, in particular in the UK and in the British Isles region. The fast frequency response is having a lot of success and being very much used, not only by renewables, but also by storage. And so in particular from the, let's say, IRENA point of view and the contribution of renewables, it's important to see what wind and solar can provide in terms of these new services. Final slide, key takeaway. So implications of inertia are observable, as I have showed in the initial graphs. It's very tangible to see the energy transition going on. The monitoring and continuous adjustment is increasingly key. For some time, everything was stable. Now everything is changing. Renewable energy sources can clearly contribute to system operation, as we have done with our exercises, and can also participate in the market. So market design, which was mentioned before in the presentations, is also important to adjust. New ancillary services have an increased importance during the energy transition, as mentioned before, and a topic I did not address, but which is that the control center of the future requires more sophisticated capabilities and tools in order to address all these challenges. And this is all from my side. Sorry for taking a bit longer, but I hope it was useful. Thank you very much.
Thank you very much, Mr. Silva. You talked about active control and reactive control, and you talked about the auxiliary services we need in the new situation. So are there any questions for Mr. Silva? If you have any questions, just raise your hand or leave your questions in the chat window. Without further question, I think that time is very limited, so shall we go to the next session? So now we come to the conclusion. May I give the floor to IRENA?
Thank you very much, Huming, and thank you so much for all the interesting presentations. It has been a very long and intense morning here in Bonn and afternoon in Beijing. So let me, no further ado, I will give the word for the closing remarks to our head of innovation and end-use sectors here at IATC in IRENA, Francisco Boschel.
Thank you very much, Arina. And once again, on behalf of IRENA, we would like to thank the colleagues from CEPRI as well as SDCC for the great collaboration on this topic of grid connection codes and the launch now of the Chinese version of such a report. Also express our gratitude to all our distinguished expert speakers for providing such insightful presentations. A few takeaways from my side is, first of all, the relevance of the grid connection codes in a time where we have the evolution of power systems from a technology perspective, but also from a regulatory perspective and a system operation perspective. All of this driven by the increase in the share of renewables and particularly variable renewable energy sources in the power system, leading that to address how this variability can be incorporated in the system without putting in peril the reliability and the security of supply. So these grid connection codes have become a very strong tool to manage such a variability and reliability of the system. But we heard today as well about the importance of also, in addition to the technical requirements, address the market design and the regulation, something that we in IRENA have been also discussing and analyzing for the last 5 years. Maybe some of you already aware of our innovation landscape report analysis, which deals more into these topics, including issues discussed today as different geographical segregation of different nodal zones, as well as new type of ancillary services to be provided, etc. I think that we heard today also in the context of the grid connection codes, the importance to have international collaboration in exchanging experiences and knowledge on how these technical requirements are evolving. This is a learning by doing process in many cases where we have seen that some of the failures that have happened in the past in some power systems are not necessarily due to a specific technical shortages, but more due to different setting of parameters, for example, in grid codes, which of course no one knew 5 or 10 years ago how the power system would be required to react and how this new generation technology would be required to react. So this leads us to one of the messages from this analysis that is been launched today, is that we know that at the moment we are in a learning by doing process. There may not be a perfect grid connection code that can be set from the beginning, but this is an evolution and evolving process. So there is, as some colleagues said before, it's better to have an imperfect grid code than not grid code at all, and then evolve involving all the different stakeholders. With that, I would like to once again thank all the speakers, partners that joined today to this event. And from IRENA's side, we reassure all of you that we will continue doing our work to support our member countries with the best practices and guidelines to integrate renewable electricity in power systems, and also expanding our cooperation with all our partners, including CEPRI and SDCC. Thank you very much.
Thank you, Francisco. For the closing remark from CEPRI, I hand it over back to Huming. Thank you.
Thank you, IRENA. Let's welcome again Mr. Li Peng to deliver the closing remarks from CEPRI. Thank you, Mr. Francisco, ITC, and experts, scholars, and young participants from all over the world. At today's webinar, we shared the advanced ideas and best practices from all over the world's renewable energy development, had fruitful discussions, and successfully met our expectations. Of course, due to the time, we didn't have time for an interactive Q&A session. Here on behalf of the CEPRI, I would like to express my heartfelt thanks to the ITC for your strong support and help to this webinar, and to all of the guest speakers and technical presenters. We have benefited a lot from the wonderful presentations and your expertise. But also like to offer our thanks to the strong support of the State Grid Corporation of China, Nestor, DII, and SOE, Imperial College London, Tsinghua University, North China Electric Power University, EDF China Research Center. I also like to shout out to Dr. Zhang Huiming from CEPRI and our colleagues from the International Department. You have done an excellent job in preparing for this conference, making it possible. There are also many experts and scholars in international organizations that I would like to thank. Thank you for your attention, because the issue we face is from all over the world. Carbon peak emissions and carbon neutrality brings an extensive and profound economic, social, systemic change. To solve many of the current global challenges, science and technology innovation is a key. Pragmatic and efficient cooperation is also vital. Special thanks to Mr. Francisco for his strong support to our cooperation and his affirmation to the result of this early stage of our partnership. Our organization share many common goals and technology innovation research practices in the field of renewable energy. CEPRI is willing to further expand our cooperation with IITC on the basis of existing technical exchange, cooperation research, staff training, and joint information campaigns. We hope to enhance the value of the IITC CEPRI cooperation platform with the SGCC IRENA MOU framework. At the same time, we are also willing to strengthen technical exchange and international cooperation with our counterparts from across the world attending today, explore win-win cooperation opportunities, and jointly contribute to the global energy, green, and low carbon transformation. Thanks again to the IITC and all guests and friends in attendance. Thank you. Thank you, President Lee. I would like to thank again my colleagues from CEPRI and colleagues from IITC who contribute to the Chinese version, translating, proofreading, and publishing. I'd like to thank for the organizer and planner of this webinar and all of you in attendance. Finally, I'd like to announce today's webinar closed. Thank you.